Hello, my name is Reese Allen, and this is my Lab 3 final submission. So as an introduction to Lab 3, it mainly focuses on magnetic fields, and more specifically, the magnetic fields of the Earth in a magnet. So throughout the experiment, the basics are that we had to download a Tesla meter, or a magnetic field reader app on our smartphone. The one I downloaded was Tesla meter, and it tracks magnetic fields. And the goal of the first part of the lab was to find the magnetic field due to the magnet. And later I will end up coding the glow script representation of the fields presented. So to begin the physical portion of the lab, the first thing we want to do is calibrate the Tesla meter app. So to begin, you want to keep your phone away from any other magnetic fields that may be close, so take the magnet away. And all the numbers reading on the screen will be from the Earth in the X, Y, and Z planes. So it is important to keep everything away from it because it will skew the data that you'll eventually want to track. But first, we should align the phone in the north-south direction, and the X value of the magnetic field of the Earth should be close to 0. So that's just by rotating the phone. So once you get it to 0, you want to place the magnet on the east-west axis. And it should, so based on that, whenever you move the magnet close and far away from the phone, it should manipulate that X value and change it away from being 0. And that's about it. So to continue with the physical portion of the lab, we move into the more calculation-based side. So at the beginning, I took measurements at different magnitudes of magnetic field due to the magnet. So that's the only thing in the X direction. And you can tell the whole magnitude of the magnet will be in that X plane because it's moving on the east-west axis. So this gave us this equation that the magnetic field created was a constant times r to the n, where k is a set of constants and n is some value that relates distance from magnet to the phone and magnetic field. So whenever you find the different distances and magnitudes, you end up getting a graph of ln with the magnitude of a magnetic field versus ln of r. And that equation graph shows us that ln of k equals negative 13.848. And that our constant value equals, which means that our constant value equals 9.68 e to the negative 7. And n was that slope on the right, and which is negative 2.49. So the value of k ended up letting us solve for the magnetic dipole moment because you're just setting it equal to a set of constants. And so we ended up finding that mu equals 4.84. So once you know this, we can use a generalized magnetic field equation to solve for magnetic field at any point, and we ended up using this in the glow script code later. And then one more part of the physical portion is finding where, at what distance is 100 microtesla magnetic field, and where we had to find where that was recorded at what distance, and that was my d perp value. And that's the rest of the physical portion of the lab. Okay, now for the models of the lab, we move into the glow script coding section. So there's a link to my glow script right here. And then going back through some of the code, the things I had to manipulate mainly were I had to enter my mu value that I calculated, the d perp value, and the formula for b that I went over earlier. And then I had to create a scale value for the arrows so they would show up right. And then I had to put in these observation locations that you can see in my model, where the two orange arrows are on axis and the blue arrows are perpendicular axis, and then this pink or purple arrow is 45-degree angle. So after putting in the observation locations and finding the magnetic fields, I had to create arrows for the magnetic field at each observation location. And the last part was just finding that last arrow for the 45-degree. So moving toward to conclude the lab here, there's two main questions that we wanted to answer. And the first was, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? And how would your results have changed? So your results would have changed because the magnetic field of the Earth would not be compensated for without calculating it. And it would be skewed a bit because the Earth's field would manipulate the magnet's field, which is what we were trying to find. And then the other question is, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? Basically, this would just create a stronger magnet, so the measurements would double, and it would have basically a double or twice as strong magnetic dipole moment.